one last thing that I would like to discuss that is specifically important for linear approximators would be feature selection. Right? If we assume a linear function approximator, we need to define relevant features in order to represent a state, right? So for the Pac-Man case, we saw an example where we said, well, maybe we should consider the distance to the ghost and maybe the distance to the closest food pellet, or how many food pellets are still left and stuff like that, right? You can think of other features that are relevant to represent a state, for representing a state. But each domain will probably require different high-level features, right? For instance, Vabhav, what features would you use for this domain? For, I don't know, what is it? Driving domain? Racing domain?
My speed, direction, distance from the lane, distance from the center.
Right, alignment with the road, right? Yes. Stuff like that. For the breakout domain, probably ball location.
How many tiles are left?
Right, tiles, their location, the location of the pen.
Yeah.
Pen? How do you call it?
And its direction and speed.
Right, and speed, stuff like that. Right. So, but the important thing to note here is that features, or the high-level features, are domain dependent, and usually they require some expert knowledge. That is, our discussion now that I just had with Vabhav, well, it mainly relies on the notion that we actually know the task in each one of these domains, right? But for a domain that we don't know nothing about, it will be hard for us to provide reasonable features. And so, of course, that's not very AI to ask an expert for the correct features. And we would like to move towards automatic feature extraction, or some general learning approaches that can provide us with the correct feature extraction, with the correct features. Right? So at the end of the day, we can consider a game state, for instance, for the breakout game here, just as a pixel matrix over the entire screen. So the raw data would be of type, for each pixel 7,3, in coordinate 7,3, is RGB 000, which is black, for instance. And from these features, all of these pixels, we need to extract some relevant high-level features, such as the ball location, ball speed, ball direction, pen location, and so on. And then you might ask yourself, okay, so how can we translate these low-level features, like pixels, into relevant features? And how can we do this automatically, right? So several approaches were presented along the years. For instance, as different functions that mix all of the low-level features in the hopes of creating relevant high-level features. So some way to encode features that was used in the past were polynomial functions that use different polynomials to construct new features from all of the new high-level features from the existing low-level features. Other approaches that were presented rely on Fourier transformations, which are general approximation methods to represent. They are able to represent any feature that you'd like, but they usually also represent a lot of irrelevant features. I have the mathematical definitions here, but they are not super important because we'll see more recent state-of-the-art approaches for feature extraction. Okay, so there are also some other approaches which I didn't define, but they also appear in the book that people used before, such as coarse coding, tile coding, radial basis functions, and so on. These are all, they appear in chapter 9.5 in our textbook. You are more than welcome to read about those. At the end of the day, each of these approaches define a set of features. Some of the features that they will produce are useful, some of the high-level features, right? They mix and match low-level features in the hopes of creating useful high-level features. Some of them will be useful, but a lot of them will not be useful. Right? For instance, there is a polynomial or Fourier function that translates pixels into pen location. There is a way to do that, but it eventually will be a needle in a combinatorial haystack, right? You'll get a lot of high-level features that are irrelevant, right? While having some that might be relevant. Can we do better? Is there a better approach to do feature selection? Vav, is there a better way to do high-level feature selection?
How about we use another approximator?
Another approximator? How about, so these days we commonly use deep neural networks. So deep neural networks are very good in extracting features, and then you can view the last layer of a deep neural network as just a linear function, transforming these high-level features that you learned into an approximated value. Q value, state value, and so on. Okay, so deep neural networks are actually these days work much better in most domains than all of these previous approaches. So we'll concentrate on using deep neural networks. Also following the name of this course, right? We're doing deep reinforcement learning. So we'll mainly use deep neural networks to do high-level feature extraction, and then the last layer we can view it as a linear approximate. The last layer of the neural net. Okay, but we'll start discussing deep neural network in our next topic.